Okay, so welcome everybody to the last session of the day. So the first speaker of the session is Rhiannon Morris from the University of Leeds. So Rhiannon, you can share your screen.
Okay, thank you. Can everybody see that?
Yes, we can. Thank you very much.
Thank you. Hi, I'm Rhiannon Morris, and I'm a PhD student at the University of Leeds. My project is modelling the organic and inorganic interfaces of urinary calculi. So why kidney stones? They affect around 10% of the global population, with a higher prevalence in the US, Middle East, and Japan. The kidney stones are a recurrent problem, and after a first kidney stone, you're 40% more likely to get another, and after a second, 60% more likely to get a third. So this can mean that one patient can have 6 or 7 kidney stones in their entire lifetime. So a study was done, and it estimated that kidney stones cost the US over $5 billion annually. And there's no real solution for kidney stones. Mostly in the NHS, they prescribe water tablets, and that's the only real solution. So people have to go in for scans to make sure they've got no stones. So the kidney stones are formed by a solid buildup of crystals that have been separated from the urine and built up on the inner surface of the kidney. And then what happens is they travel down the urethra and exit out the bladder. So kidney stone composition. Around 80% of stones are either calcium oxalate or calcium phosphate stones, with struvite stones accounting for 10 to 15%, and these are commonly called infection stones because these are normally found with people that have got a kidney stone from a urinary tract infection. We also have uric acid stones, which account for around 10% of stones, and these are more common in men than in women. And we have cystine stones that compose around 2% of all stones. So in my work, we're going to focus on the calcium oxalate stones, as these are the most common type. And I do this by using geometry optimizations. So all my calculations are carried out in CASTEP, which uses density functional theory. And my optimizations are used the on-the-fly pseudopotentials generated by CASTEP and a plane wave basis set with a cutoff energy of around 900 electron volts. So because CASTEP only moves the geometry optimizations into a local minima and not into the global minima, we've also run ab initio molecular dynamics simulations so that I can sample more of phase space. So with these calculations, I've used a cutoff energy of 390 electron volts to give a balance between computational cost and accuracy. And again, I've used PBGGA with the TS dispersion correction. So with the ab initio molecular dynamic simulations, I've used a MVT, so I've kept the constant volume and temperature, and I'm using a Nuss-Hoover thermostat with the temperature set at around 309 Kelvin, which is around the same temperature as a kidney, and I'm using a time step of 0.5 femtoseconds. So with each geometry optimization, I work out the absorption energies for each system, so I can compare between the systems and see if it's favorable for this absorption to work. So I started off with constructing calcium oxalate surfaces, and there's 2 different types of calcium oxalate. You have calcium oxalate monohydrate and calcium oxalate dihydrate. So I've constructed the calcium oxalate monohydrate surfaces based on crystal structure data from Tazuli, and these guys, they got a kidney stone and they got the crystal structure directly from the kidney stone. So I constructed the COM010 surface, as this was seen to be observed in experimental publications where they got kidney stones to grow in a laboratory. And for the calcium oxalate dihydrate surfaces, I built these surfaces from crystal structure data from Adsorption, and they also used a kidney stone to get the crystal structure. and I built the COD 110 surface to perform simulations. Again, it was readily observed in experimental publications. So after I built the surfaces, I absorbed calcium oxalate onto the surfaces to see if the surfaces were susceptible to growth. And they were. So this graph here shows on the calcium oxalate monohydrate surfaces, I built the 100 and the 010, which is shown in yellow and green. We selected the 010 to do further absorption studies on, as this was more susceptible to growth than the 100. And with the calcium oxalate dihydrate, I constructed the 100 in blue and the 110 in red. And again, we saw from this data that the 110 was more susceptible to growth, as it had around a -6 electron volt absorption energy. So this surface we selected as it would be more likely that an absorbate would potentially bind to this. So with the absorbate selection, I looked at publications of what constituents were at higher concentrations in kidney stone sufferers' urine. I got a range of data. So I got proteins. However, because of the scale of this work, I took these out of my search criteria because they'd be too large to model using ab initio ND. So I focused on small molecules and lipids, and I found that the lipids that were at the highest concentrations in stone sufferers' urine were sphingomyelin, which has this structure and a very large tail group. We also have phosphoethanolamine, glucoribosicides, which have 2 long tails and a glucose head group, and phosphocholine. So the cell membranes of the kidney stones of the kidneys is generally where the kidney stones attach to. So as the calcium oxalate is moving throughout the kidney tubule, it attaches onto the side of the cell membrane, and that's how the stone starts to form. So we decided to look at what phospholipids were on the outside of this cell membrane. From publications, we found that it was phosphocholine and sphingomyelin, which were on the outside of the cell membranes. And because the sphingomyelin has a rather large tail group, we decided to focus on the phosphocholine to start off with, as it was just easier to model. So the idea is that the calcium oxalate comes into the cell membrane and binds to the phosphocholine. And then we wanted to see whether this would cause a further calcium oxalate to then bind to this and cause the stone to grow. So I decided that in order to be able to do this, we'd see if we could get a phosphocholine molecule to absorb onto the calcium oxalate monohydrate surfaces. So we did a small molecular dynamics of this, and we saw that it did in fact bind after 2 picoseconds with a negative absorption energy of -2 electron volts. And this was mostly driven by the formation of the ionic bond between the oxygen in the phosphate group to the calcium on the surface. We did the same for the calcium oxalate dihydrate surfaces. And when we did this, the phosphocholine came in and bound with a much lower absorption energy. And after 6 picoseconds, we found that it bonded with about a -5 electron volt absorption energy, which shows that it's quite favorable for the phosphocholine to bind onto the COD 110 surface. And these again were moderated mostly by the ionic bond formed between the oxygen in the phosphate group and the calcium on the surface. And again, also there were hydrogen bonds present from the phosphocholine to the calciums and to the oxygens on the surface. So I thought, what would happen if we placed a phosphocholine in between 2 COD surfaces? We found that the surface, in fact, encapsulates the phosphocholine and tries to redefine the crystallographic structure of the surface. Oh, sorry, that's gone. Oh yeah. So you can see from this short video that the surface, in fact, pulls away from the phosphocholine at the start and then moves back in as if trying to like redefine the crystal structure. So when we broke this simulation down, we found that it was highly favorable for the phosphocholine to bind to the cod surface. And this model, in effect, models the fact of a phosphocholine moving through the tubule and a pre-nucleated crystal of calcium oxalate dihydrate attaching to it and causing it to bolt together and start a stone growing. So after 6 picoseconds, it was around a minus 14.5 electron volt absorption energy. And this again is mediated by 2 oxygen calcium ionic bonds, which have a molecule population of around 0.15 and 0.13, which shows that they're fairly strong. And then there are numerous hydrogen bonds between the phosphocholine and oxygens and hydrogens in the surfaces. So when I compare this data to the growth, we modeled the growth, you can see in the bottom left of this screen, the diagram which I showed at the start, which was the simulations of the calcium oxalate binding to the surfaces and simulating the growth. And then we have this phospholipid data on the top right. So if you compare the COD110 phosphocholine absorbing onto this COD110 in the blue with the red line in the calcium oxalate graph on the bottom left, we can see that it's actually more favorable for calcium oxalate to bind onto the COD110 than it is for the phosphocholine, as the calcium oxalate was binding with around a minus 7 electron volt absorption energy, whereas the phosphocholine bound only with about minus 6. But when we had the phosphocholine encapsulated, we got a much lower absorption energy of around minus 14 electron volts, as I just discussed. So we're going to continue with this work and see whether it is the encapsulation of organic molecules that cause the stones to grow, rather than the stones just growing from calcium oxalate traveling through the kidney tubules. So the outcome so far is that we've successfully modeled the growth of calcium oxalate monohydrate and calcium oxalate dihydrate surfaces. And we've shown the impact of phospholipid phosphocholine on both the calcium oxalate monohydrate and calcium oxalate dihydrate surfaces. And I've also shown that the stone growth can be promoted when phospholipids are encapsulated by calcium oxalate dihydrate surfaces. And the driving force for this is that the crystallographic waters are attempting to redefine the crystallographic structure. So the next steps of this work would be to see if the calcium oxalate can replace a bound phospholipid on a calcium oxalate surface. And if it can, will this be different between calcium oxalate monohydrate and calcium oxalate dihydrate? And whether the calcium oxalate monohydrate surface, could that also encapsulate the phosphocholine, or is it just the calcium oxalate dihydrate surface which encapsulates the phosphocholine? And I'd also like to investigate whether any other phospholipids could behave in the similar way. So like we discussed the sophincomyelin, see if I can find a model for this and see if it behaves in the same way. And if so, then are these lipids that are at higher concentrations in the urine actually causing the stones to grow? And I would like to thank all my supervisors for their support and encouragement. And I'd also like to thank our close collaborators, that are the nephrologist and the urologist at St James's Hospital, Leeds, and the clinical scientist there, which has given a lot of insight into how kidney stones form and the procedures they use in hospitals to treat kidney stones, and also have donated some stone samples, which hopefully I'll be able to go into the lab to do some microscopy work on. Thank you, and if you have any questions.
Thank you very much, Rhiannon, for this interesting talk. So if you have any question, please put them in the QA tab. So at the moment there are none, so maybe, no, okay. Aline, you have a question? You're physically raising your hand.
Yes, since I have the microphone already. So, very nice talk. I have a question for you. You said that you did ablution, some of them are pretty short, 2 picoseconds.
Aline, sorry, your sound, there is like a background,
Okay.
some background noise.
I know. Let me check.
Well, since maybe in the meantime, I can ask, in your calculation with the molecular dynamics, where you looked initially if the lipids would adsorb on the surface, what do you have here as a background, as a medium around in the calculation?
I don't actually have anything in the background. It's just in vacuum at the moment. We did discuss about adding water in, but then from previous work, we've seen that the interactions are then just mediated through the water. So we decided to exclude the water mostly for calculation cost time.
Right. But maybe having vacuum, I've found that sometimes having vacuum overestimate a bit the adsorption energy, because there is nothing else the molecule can interact with, so it actually interacts with whatever it founds as soon it found. So, but okay, here it is. Aline is back. Okay.
So, do you hear me better now?
Yes.
Okay. So my question was, when you run that molecular dynamic simulations, you said that you ran 2 picoseconds and nothing happened. Are you sure that you run long enough, or are you sure that nothing happens because nothing really happens, or it happens very seldom?
So I initially ran 2 picoseconds and nothing really happened, but I'm still continuing these calculations, so it is still running at the moment, just to double check that nothing is happening. But yeah, I'm aware that 2 picoseconds isn't a very long run, so it is still running at the moment.
But do you expect anything to happen?
No, I don't think I would expect anything to happen. Based on other data, I think it will just not absorb onto the surface, but I'm going to continue just to double check. Normally in the first 2 picoseconds, if it doesn't absorb on, it just keeps floating in the vacuum at the top. So I expect that to happen, but I will run for a full 10 picoseconds to double check.
All right. Okay. Thank you very much, Rhiannon.
Thank you.
We can move on to the next speaker, who is Paolo Restuccia.
Okay, just a second. That screen. Can you see my screen?
Yes, great. So the next speaker is Paolo Restuccia from Imperial College London.
Hi. Hi, everyone. Thanks for the introduction. I'm Paolo Restuccia, and I will talk about the creation of a predictive model for absorption, molecular absorption through ab initio simulations. So just to give you a brief introduction about absorption, the absorption of molecules, atoms, and ions is a process that involve the addition of these components like atoms, ions, and molecules from a generic phase that could be either a gas, liquid, or solid phase to a specific surface. So here is just a pictorial representation of some water molecule in the gas phase. And through chemical or physical interaction with the substrate, they adhere, they attach on the surface. They can either be as a simple molecule, or they can dissociate over this molecule. So you have two different components in the adsorption process: the adsorbent, which is the substance which is adsorbed on the surface, in this case water, and the adsorbent, which is the substance on whose surface the adsorption occurs. In this case, this gray area here is kind of generic substrate. The driving force for the absorption is a surface phenomenon, and this is due to the presence of unsaturated atoms on the surface. So this is again a simple example of a copper dioxide 111 surface, in which you have the let's say bulk atoms here that are completely saturated, whereas here on the surface you have unsaturated, for example, oxygen and copper atoms. These atoms have dangling bonds, so unsaturated bonds that let's say increase the attraction of the surface, and so they can interact with molecules present in the environment. So the general rule of thumb for the adsorption on surfaces is that you have unsaturated atoms in the surface, which leads to a higher surface energy, which leads to a higher absorption for absorption energy. There are many applications for absorption. There are many research fields in which this process is essential. For example, heterogeneous catalysis, in which the molecular absorption is the driving process of this phenomenon, in particular the dissociation of molecules over a metal substrate like gold or platinum. It can enhance the catalyst properties of the substrate. Then the study for corrosion inhibitors. You have to know that the worldwide cost to prevent corrosion is around $2.5 trillion per year. So the study of corrosion inhibitors that can inhibit and prevent the destructive corrosion of, for example, iron pipelines, it's very important to both mitigate this huge cost and also to mitigate environmental costs. And finally, also the study of lubricant additives, especially in the recent year, the development of microelectromechanical devices requires us to find new solutions for friction reduction due to the limited dimensions, and so studying molecular additives in the base oil or molecular additives that can be attached on these devices that can enhance the sliding between the surfaces, the interfaces, or for example, the gear that usually you can find in these devices is essential to increase their sliding properties. Why is so important to study and to find a predictive model for adsorption? This is something that people was looking around in the past couple of decades, and the most important things about finding a predictive model for adsorption for molecular adsorption is the possibility to find effective descriptor for explaining the microscopic origin of the adsorption processes. So just the idea of answer to basic research question of why molecules attach on the surfaces and why they, for example, dissociate on a specific surface and not on another. Another important point is that predict the adsorption energy of molecules or functional groups on surfaces is very important before running very expensive first principle calculation or performing a laboratory experiment. So it will be very important to predict the adsorption energies in a matter of minutes instead of running heavy, for example, DFT calculation that sometimes requires many CPU cores, so many computational hours. And so that will be very important. Also because for materials design purpose, it will be very interesting to understand how to create new molecules that can either replace or improve current molecular additives, and having some kind of predictive model can allow us to compute this quantity, the adsorption energy, in a matter of minutes, instead of computing the adsorption energy of a new molecule over a specific, over different substrate in different configurations that requires a lot of time and effort. So the first step to create such a model is to find the proper descriptors that can allow us to have an effective model. So in the literature, you can find several of these kind of simple equation with just simple linear equations. One of the most effective is this model proposed in this Science Advanced paper from 2019, in which you can see it's a simple linear relation with just 4 coefficients. And the authors identify these the 3 main coefficients as the local cohesive energy, which is a term which is defined in the paper and gives you an idea of the cohesive environment around the adsorption site. They also consider the middle of the molecular gap, so the HOMO minus the LUMO divided by 2 of the absorbed molecule, so to take into account the presence of the adsorbate, of course. And finally, they create this, they computed this MADs term, which is a kind of absorption energies of a molecule composed by just a single metal atom of the substrate, of the considered substrate for the adsorption process, and the molecular functional group that is attached on the substrate. And this is computed by ab initio calculation. So the main idea is to perform linear regression with the machine learning algorithms in order to identify these different coefficients and to create a model to predict the molecular adsorption. So this is just an idea of what they done. This is the training and testing part of their work. So they computed here on the x-axis, this is the DFT binding energy, the actual DFT binding energy of these functional groups like methyl, carbon monoxide, and hydroxyl groups over some several noble metal substrates, so silver, copper, and gold. On the y-axis, instead, you have the prediction of the adsorption energy using the equation that I showed you before here. And as you can see, the correlation is quite good. And so this is an interesting way to proceed to creating a proper predictive model for having the computing the adsorption energy. Of course, there are some, as any model, there are some limitations. They created this model in a way that they only consider the adsorption in the on-top site. So this, of course, limits the possibility to effectively predict the adsorption energy in other adsorption sites, which sometimes is very, very important because the adsorption energy can be lower in other adsorption sites rather than the on-top. And also the training part is performed only on noble metals, nanoparticles, or slab surfaces. So in this case, just silver, gold, and copper. And this, of course, narrows the range of effective prediction. As an example, you are not considering transition metals. So there is plenty of room to improve this kind of approach, and we try to do something conceptually similar, but just to consider something different, starting from the actual equation that we use, in which we consider different terms. So in particular, we are not considering a local cohesive energy, but a bulk cohesive energy, in order to consider better all the different surfaces that we consider in our study. Then, instead of just taking into account the middle of the molecular band gap, we computed the difference between the substrate work function and the molecular middle of the band gap. And this is a reasonable assumption that arises from the frontier orbital theory, in which usually you have that the molecules want to align their molecular orbitals with the Fermi energy of the substrate. And so this difference is quite important to take into account. And then again, we consider an ab initio term that we just simply call molecular binding energy, which is defined in different ways in order to try to improve the model. And I will show you in a while how it's performed. If you're interested in all the computational details, we publish this work on arXiv, and this is the reference. So just to give you an idea on how this MBE term is computed, we start with a geometry, a quite simple geometry that resembles the one that the authors of the Science Advanced paper used in their work. So a simple metal atom that resembles the surface. In this case is a copper atom. With that, and in this case, a chlorine atom that resembles the adsorbate. And here is the formula with which we compute this MBE term. In our case, it's a summation of all the possible fragments that you are considering the adsorption process of the energy of this complex of the, let's say, the molecular energy computed by, for example, DFT calculation, minus the bulk energy of the metal substrate in this case, minus the chemical potential of the molecule in the gas phase. In this way, we have a very consistent set of reference value. So we can compute all these terms, MBE terms, in a very consistent way, one to another. And the other point is that using this definition for the chemical potential allows also you to consider, in this case, we just consider the gas phase just for the sake of simplicity, because we want to study the effectiveness of this approach. But there is also the possibility to consider a chemical potential in, for example, in a solution. So something a little bit more complicated that could be something more similar to actual experimental conditions. So what we have done next is doing something similar. So performing the training through machine learning algorithms of this formula, the formula that I show you here, with, again, the DFT calculation of the DFT absorption energy of several molecules, ranging from simple diatomic molecule to, let's say, slightly complex one like water and carbon dioxide on several substrates, like noble metals again, but also aluminum, iron, and vanadium, iridium, and platinum. So try to range a little bit more out of the noble metal substrate. And again, we perform this regression with the predicted value of the absorption energy. As you can see here, this first approach is not good at all, because we have a correlation coefficient very, very low, around 0.2, and with a very, very large mean absolute error, about 2 EV, and you can also see from the plot, this is not good at all. So what we try to do is we try to improve the model, and instead of consider just this kind of molecular approach in computing the MBE, we try to use a kind of cluster approach. And here again is an example for the chlorine on copper system. And here the single metal molecule atom is replaced with a kind of cluster, a small cluster, that resembles the adsorption site of the system. So in this case, for example, this system resembles the adsorption of a single chlorine atom on a hollow site of a copper 111 surface. So to take into account the different system, we also slightly modify the formula for the calculation of the MBE term. And in this case, we are not computing the bulk energy for the metal, but we computed the energy for the metal cluster, the isolated metal cluster, when we computed the ab initio formula. When we use this approach, we can see that we have a great improvement. So now the correlation coefficient is around 0.83, definitely better than before. And also the absolute error is more than half. So now it's around 0.9 EV. So what we try to do next is just to go a little bit larger, and we try to use a larger cluster. In this case, the cluster again resembles the absorption of a chlorine atom over an hollow site of the copper 111 surface, with just using 10 atoms instead of just 4. Try to resemble better the absorption and the absorption substrate. One at this point could ask why just performing this calculation when you are trying to run ab initio calculation of the slab configuration. The main idea of this approach is that we can compute this MBE term once and for all for several functional groups over several substrate, and this can be collected in a database. So when you want to perform another calculation of a new molecule over a certain substrate, you can just check if that specific functional group has already been computed, again, once and for all, and then you can predict the absorption of this specific functional group, instead of computing an actual slab configuration that sometimes, especially for complicated substrate, like, for example, iron, could take a very, very long time. So when we are using this larger cluster approach, we have another increase of the correlation coefficient. Now it's around 0.94, which is very, very good. And also the mean absolute error is now around 0.5 EV. So this is just the training part. So we just train the model to be effective, to be consistent, reasonably good in the prediction of the absorption energy. Now what we try to do next is try to validate the model. So try to compute, to predict the absorption energy of some calculation that we have never done, that we have never done before. And to do that, we use the absorption energy taken from a database. which is the Catalysis Hub database, which is a quite large database of more than 100,000 reaction energies, so there are a lot of them. And we test our model with more complicated, let's say, molecules, just a little bit larger molecule, like, for example, methane, ethane, ammonia, and different nitrogen oxides on several substrates that we have, didn't compute before. So, for example, cobalt, nickel, scandium, and yttrium. And we compute a total of 80 reactions path. As you can see from this validation test, we have a very, very good correlation coefficient, again, 0.93, so again, very, very high. And again, the mean absolute error is not so large, especially just to give you an idea, we range the adsorption energy between minus 15 EV to plus 6 EV. So having an absolute error of around 0.7 EV is quite reasonable with these very, very large values for the adsorption energy that we have found in these specific systems. So just to give you some...
That's fine. You asked me to tell you. Oh, okay.
Perfect. So just to give you some conclusions, so we found that this model can give a reasonable estimate of the adsorption of small molecules on metal substrate with, let's call it reasonable descriptors, so descriptors that can be are based on the physics and chemistry of the system that we are studying. And the interesting point is that considering the large values of the adsorption energy, we can clearly understand if the molecule can dissociate or not over a substrate. Of course, a downside of this is that in the weak bonding region, so for molecules that have an adsorption energy of around plus minus 1 eV, this prediction is around the margin of error of the model, so we have to be quite careful in that region. And of course, we have to check if we can improve the model to predict better that region of adsorption energy. So these preliminary results suggest that the model seems to work reasonably well. But of course, we need, first of all, more testing, because performing more testing can allow us to understand if everything is fine for a wide range of adsorption adsorbate, so for a lot of molecules, or if there are some systems that have to be treated in a different way, for example. And also, this kind of approach, with this kind of cluster approach, can be very useful also for the possibility to use the model and to implement the model with more complicated substrate. Because one of the let's say, biggest problem in these works, in the previous works, is that usually the system involved are simple metal or metal alloys. There are very, very few works about, for example, the adsorption on oxides and carbonates. And of course, it will be also very useful to study also more complicated functional groups that can be used in either, for example, as a corrosion inhibitors or as a catalyst or as a lubricant additive. So this is a starting point to create a more complicated model that can predict the adsorption energies of more complicated molecule on more realistic substrate. So to conclude, I would want to thank the funding and technical support from BP-ICAM for the funding and the technical support. Also, I want to thank Imperial College for the use of HPC facilities, and all of you for your attention.
Okay, thank you very much, Paolo, for the interesting talk. So we have time for a very quick question. Yes, there is one.
I have to share my screen, I guess.
Yes, before. All right, here. Nice talk. Perhaps I miss it, but what is the reason you are using a fixed definition for your model with the optimized coefficients rather than using, for example, CISO approach which does not have human bias on the observables included?
That's a very good question. This is something that we definitely want to do next. We start with that because we work out quite a lot to find a reasonable descriptor by hand. And of course, that was quite time consuming. It takes a lot of time. And then we find this specific paper and we try to replicate the same result, but since we didn't obtain, as I show you, the first example, just by using their definition of this ab initio term for describing the interaction between the molecule and the substrate, we were curious to see what happens if we want to consider something else, a little bit more complicated as a kind of cluster approach. One of the next steps that we want really to explore is to try to, let's say, make it automatic to check the different several descriptors in order to not be biased, so to find the proper one. And also by using this relation, this machine learning algorithm, this an ordinary least square algorithm. So it's quite simple. You can also obtain the p-value of the different coefficients, so you can really understand which are the values that are the most important in your calculation. So
thank you.
This is definitely.
Okay, thank you. Sorry, because we are running out of time. So thank you very much for your talk. And so the last speaker of the day is Juliana Morbec from Keele University. So Juliana, if you want to share your screen.
Yes, let me see how I would do that. Here.
So there is a.
Okay, I just found it. Now I have. It's kind of different from everything I have been using.
Yeah.
Yes, PDF here. Hopefully. Yeah. Yes.
Oh,
I think that works.
Fantastic. Okay, so the last speaker is Juliana, and please.
Okay. So good afternoon, everyone. My name is Juliana Morbec. I'm from Keele University, and today we will talk about interactions of organic molecules with inorganic materials. In particular, we are going to investigate, to look at the coverage effects and the role of Van der Waals interactions. So let me see if I can. Okay. Oh, yes. So, well, the motivation for that is that when you combine organic and inorganic materials, you can have, you can try to do a synergy of what to have good about organic materials and of what to have promising from inorganic materials. And maybe you can find at the interface properties that you cannot find in the isolated systems. In this particular talk, I will talk about interactions of anthracene and pentacene molecules with metal surface. And these molecules, they are interesting because they have high carrier mobility. They also have excellent photoluminescence and electroluminescence, and they are very good for using light-emitting diodes and field effect transistors. So the idea here is that you can combine this kind of molecules. They have very good properties for optoelectronic applications with metal surface that you usually will have metal surfaces used as a contact inside of kind of systems. So, well, we do dense functional theory calculations. So you use FHIM's codes. I don't want to bother you too much with the details of the codes. You use exchange correlation functional like PB, but here what is important is the Van der Waals methods that we use. We sure need to include Van der Waals to describe kind of type of systems because PB exchange correlation functional doesn't include long range Van der Waals corrections. And so here you kind of try to investigate how the different methods that's available in the literature, how they perform and how good they are for this kind of systems. So here I mentioned that we use what I call Van der Waals surface method. This Van der Waals surface method, it uses is a pairwise Van der Waals methods, you just work with two elements, but you consider the dielectric function of the surface. You don't consider you consider the difference of the atom as in the bulk system or as in the surface system. And so here we include the dielectric function of the surface. And you can also implement it self-consistently. Usually you use Van der Waals interactions, and it is implemented as a correction at the end of the calculation. So you don't include Van der Waals interactions, for example, when you are doing calculations of density of states or charge density. But when you use self-consistent Van der Waals interactions, you include Van der Waals in each of the self-consistent step of the density functional theory calculation. And so you can later on have Van der Waals included also when you are computing, for example, density of states or charge density. And another method that we use here, as I said, Van der Waals surface, it's a pairwise method, so you include two bodies at any time, but you can also include how the effect of many body interactions will have in the Van der Waals interactions. So you can use also the many body dispersion method that uses the many body idea. So here we are including the many body response in the Van der Waals energy. And the many body, the atomic response is represented by quantum harmonic oscillators. So, as I said, we investigate anthracene and pentacene molecules on metal surface. Here I'm going to talk about silver surface. And for anthracene molecule, this is a very small molecule, have just 3 benzene rings, and so you use a small cell here, and you consider that we have one monolayer coverage by the distance of this the molecules in this kind of systems. And for pentacene molecules, it's a larger molecule. You have 5 benzene rings, so you have to use a larger cell to consider one monolayer coverage. And we include different sites where the molecules cannot be adsorbed. So what we observed is that, for example, for anthracene molecule, when you include, this way I have results from PBE calculations and results for Van der Waals surface, and when you have just PBE calculations, you have the molecule tilted with respect to the surface and large binding distance. But when you include Van der Waals interaction, because in the inclusion of Van der Waals interaction, you bring the molecule close to the surface, close to the experimental result we find, and the molecules also stay parallel to the surface as we expected. For pentacene is the same thing. The inclusion of Van der Waals interaction brings the molecule close to the surface as we expect. If you see here, it's a better view of what's happening. If you see this black curve, it's when it's the results when you don't include Van der Waals interactions. You see the molecules, they don't bind to the surface because you really need Van der Waals interactions here. And then when you include Van der Waals interactions, you see the molecule binds to the surface with a larger binding energy and a smaller binding distance. And well, you can also split, consider different parts for the energy. And what you observe here is that you have the binding energy comes from the deformation of this lab, because of when the molecule sits in the lab, for the formation of the molecule, the interaction between molecule in this lab, and the interaction between molecule and molecule. And you see the largest contribution for the binding energy is the interaction between molecule and substrate. And for both systems, if you include Van der Waals interactions. When you don't include Van der Waals interactions, you see that the contribution from the interaction between molecule and substrate is very small. And also, we'll look also how the work function will change when you include Van der Waals. When you include the molecules, the work function changes, where the work function of the surface change when you include the molecule, and there is a reduction in energy. Reduction of the working function when you include the molecule. And you see that the reduction of the work function is much larger when you have anthracene molecule than pentacene molecule. And this is because anthracene molecule is physisorbed in the surface. We don't have the interaction between anthracene molecule and the surface is very small, and so the pushback effect of the surface makes the large reduction of the work function. While in Pentacene, you have the Pentacene is more chemical absorbed in the surface, so you have the pushback effect, but you also have a charge transfer between molecule and surface, and that's what makes the reduction of the work function smaller. And you can see here that, for example, for this is density of states, this is the density of states of the absorbed molecule, and you see that the lumen of the anthracene is higher than, above the Fermi level, while in Pentacene, the lumen is on top of Fermi level, meaning that there is some charge transfer between Pentacene and the surface. And you can, I'm sorry, let's just pass very quickly here. And you can really see that there are some charge, this is Pentacene on the right-hand side here, and you can see this red part of the figure. They are positive charge transfer between molecules and surface. So there is accumulation of charge between molecule and surface, while on anthracene you just have depletion of charge, that's the blue part, that you don't have charge transfer between anthracene and Pentacene. So our conclusion here is that Pentacene is more chemically absorbed on the surface, so this is why the work function has a smaller reduction of the work function due to Pentacene. And you can see this here in this, this is the charge density difference along the Z direction when you go from the surface to the molecule, and you see there is more accumulation of charge here between molecule and surface when you look for Pentacene. Then there is the accumulation of charge is larger in Pentacene system than in anthracene system. And then obviously here you have density of states again, and then we have the lumen states of Pentacene on top of the Fermi level, which means there is some charge transfer, as you saw in the charge density. But this brings us to also ask how the coverage effect is affecting the Pentacene molecule, because I told you some slides ago that you can look at contributions from the formation of the molecule, the formation of this layer, but also molecule-molecule interaction. And when you consider one monolayer coverage, the interaction between molecule and molecule play an effect in some sense that when the molecules see each other, they see less the substrate. So as much interaction you have between the molecules, less interaction you have with the substrate. And so you look at that. So we start, for example, with Pentacene from a 6x3 cell that you consider to be one monolayer coverage, and you increase the size of the cell, meaning that the molecules are being far apart from each other. So the molecules should see more the substrate. And then this is just preliminary results. We're still doing work on that. But what we saw is that for binding distance, you don't see too big difference when you increase the size of the cell. But the binding energy quite increases when you increase the size of the cell. And this is due here to the interaction between molecule and substrate. You see that the interaction between molecules and substrate increase when we go from a 6x3 cell where you have one monolayer coverage and increase the size of the cell, meaning molecules will be far apart from each other. So molecules interact less with one another, as you can see this on this penultimate line here, and interact more with substrates, with the substrate. And now for the workers function, as Pentacene interacts less with substrate, is less chemical absorbed to the substrate, and then you see the reduction of the wave function is smaller too. Same goes for anthracene. You also consider larger supercells for anthracene, and you also observe that as you increase the size of the supercell, then you have less interaction between the molecules between each other, among each other, but you have stronger interaction between molecule and substrate. And the same happens for the work function. So in the initial system, you have small interaction between anthracene and the substrate. So the pushback effect makes a large reduction of the work function. As the molecule starts to interact strongly with anthracene, with the substrate, it goes from the physisorbed system to a chemisorbed system. So you have start to be having charge transfer between molecule and surface, and then we start having compensation of the pushback effect and a smaller reduction of the work function. So this brings me to my summary. I think I make it on time. So we observed here in our study of anthracene and pentacene on surface that the inclusion of van der Waals correction is crucial to describe correctly binding energies and binding geometries for the systems. And I didn't discuss very well this part of self-consistent, but I just skip very quickly there. But you saw that when you include self-consistent correction, you don't have just one little tiny effect in the electronic structure, so it's really not very relevant. But we saw that the interaction between molecule and substrate increases when you increase the size of the supercell, and mainly for pentacene, or in leading a small reduction in the work function when that's saw pentacene on the system. And so I think that's all from me today. That's too quick here. So thank you all for attending and for your attention.
Thank you very much, Juliana, for the interesting talk. So are there any questions for Juliana? It doesn't look at the moment. So maybe I can just quickly ask, so all this work is going in what direction? So now that you have figured out what is the prime method to look at the adsorption energy of pentacene on the surfaces, so do you have any application in mind? Or
No, we are trying now to understand what's happening with the coverage. We're still, this is preliminary results. We're still trying to understand what is happening when you change the coverage of the systems, and how it will affect the work function. We're still kind of investigating this part.
all right, thank you very much.